Hello, this is Deep Thoughts with Deegan, and today I'm going to be talking about a very special fractional derivative. So I'm just going to write it up here. So I'm going to have a little omega down here because I'm going to use n for something else. So the omega derivative of x to the n, where n is a constant, so it's going to be some power, e to the x with respect to x. And what's that going to be equal to? Well, I'll get there. Now, this currently is almost like a prototype for a formula. It's not 100% fleshed out yet, but I think this specific problem has a really cool pattern. And I'll get there in a second. I'll use this color. First of all, a lot of this hinges on the quick derivative shortcut that I've used many times on this channel, where we got derivative with respect to x of some function f of x. I'm actually, for this video, I'm just going to say u is the function. U e to the x is equal to u e to the x plus u prime e to the x. So a lot of this is going to be based on that. And this will work because we do have a rule for the nth derivative of both of these, right? Now, to do this, I'm just going to see what happens if I take the first derivative. All right, so this first derivative, I'm just going to keep my x to the n e to the x, and I'm going to add whatever the derivative of this is, which is n x to the n minus 1 e to the x. Now, if I do this again, I'm going to get x to the n e to the x plus nx n minus 1 plus, so that comes from here, plus n times n minus 1 x to the n minus 2 plus this again. But that's not very nice, right? That's so difficult. So what I ended up doing when I was working through this, I've been working on this for multiple hours. I was working on it yesterday. I'm wearing the same shirt as the last video because I literally just recording this like a couple hours later. But I'm just going to define some function f of x. And this function f of x is going to equal, that might be the worst omega I've ever drawn. This function f of x, I'm going to use a different color, is going to be equal to f of x. I'm just going to write it small because I'm also going to have a g of x one that I'm going to use later. It's the omega derivative, because I'm going to use that same omega, of x to the n with respect to x. Okay? Now, first of all, every time that I use this, the condition where omega is equal to 0 should equal this function itself. And it will. But if you just look at this, it'll work so far. Now, I am going to show you what happens, because if you noticed, it kind of keeps splitting off. So what's going to end up happening is I have my f of 0 e to the x plus f of 1 e to the x was my first one. Now, the derivative of this is going to be the next step. So what I can say is every time that I have something, so the derivative, I'm going to write this over here also. Whenever I have a single term like this, what I can say is the derivative of that is going to equal itself. So f of omega, we're just going to call it omega because that's where it starts, plus the derivative of that, which is going to be omega plus 1, because we're going to add 1 to that, the next derivative, f of omega plus 1. Oops, I forgot the e to the x. E to the x. I'll just keep that there. E to the x plus f of omega plus 1 e to the x. Right? So, what's going to end up happening, and the way I do a lot of these test ones, is I'm just going to create a table. So over here, I'm going to have my, I'll do it like this. So for however many derivatives I'm taking, what is going to be how many of each f of omega is there going to be? So for my first, second, third, fourth, I'll go to 5. Actually, before when I was doing this, I had like a 10 by 10 table of these. But this will work now just to show you what's happening. We're going to have 1, 2, 3, 4, 5. It just needs to be even. And off the top of my head, I'm just going to write this down and I'll explain why it works. And something cool is going to happen. It's 3, 3, 1, 0, 0. You might already notice there's something happening here. Right? I think I messed something up. I did. That's really sad. I'm just going to shift this over. Yeah, we'll go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is just my f of omega. So this is going to be the coefficient of this is basically going to be the coefficient of every single term. Because if I take this, it's going to split up into 2. So I'm just going to start with a 0 for the 0th one, I guess. Technically, also, this should start at 0. I literally just did this. That's why I'm making these small mistakes. Okay. So for 0, 1, 2, and I'll go from there. So 0, I'll go to 4 like I had here. 3, 4. 0 is going to split off into 0 and 1. And it's going to keep the 0 and 1 are going to keep splitting off into 0 and 1. Now 1 is always going to go to 1, 2. 1, 2. Oops. 1, 2. It's going to be 1, 2. 2 is going to go to 2, 3. Then we're going to get 1, 2, 1, 2, and so on. And I'm just going to keep writing them. That's 2, 3, 2, 3, 3, 4. And if you count all of these up, you will get this. I missed something somewhere, but that's the general idea. So, I think I miscounted again. That's fine. But you get the idea. And what this is, if I were to shift this to a form you've probably seen, this is Sierpinski's triangle, which I think is pretty cool. It's just actually shifted over. That's why these tables are super useful when I'm doing these, because I can see these kinds of patterns. Now, if we know that's true, I need to find a way to incorporate that into this. And the way I'm going to do that is I'm going to create another function, because I have not quite figured out how to exactly pinpoint a spot on there. So I'm going to say g of x. Actually, not g of x. What I'm going to say is g of omega and alpha is going to be equal to the alpha. I used both n and omega, so I'm just going to use alpha for this. The alpha, I guess, index, we'll call it an index, of the omega row of Sierpinski triangle. Right? Now that's a lot, but this is true. And I can put this into a summation. So what's going to end up happening is this, all of this, is going to equal something times e to the x. I want to see what's happening to this polynomial, because obviously e to the x is going to be on the outside. But I'm going to say, well, what's happening here at this h? Like, let's say h is another function. That's going to be what happens to this polynomial term. So I'm going to say h, I'll explain this in a second. H is going to equal a sum, obviously, because it's going to become a polynomial. It's going to keep getting bigger and diverge, predictably, but it will diverge. And I'm going to use j as my counter. I'm going to start at j equals 0 and go to omega. Okay. And what I'm going to do is I'm going to look in here. I'm like, okay, so for my coefficient, every single time, it's going to take whatever row we're looking at. Actually, j. We're going to look at a row. Oh, yeah. We're just looking at the top. We're looking at a row, omega, which is going to be like, all right, we're at 0 is only going to have 1, and so on. So technically, it should be omega minus 1, because it's actually shifted up from that first row. And the second part is going to be j minus 1, because it's an index, so the first term is going to be after. Actually, no, I already have j is equal to 0, so it's just going to be w minus 1, omega minus 1, j. Okay. And then from there, that's going to be my coefficient. I'm going to multiply that by whatever this f of x is going to be at omega, f of j in this case, because that's going to be whatever step this is. So I can put this all together really quick into this whole problem being equal to, hypothetically, again, I'm not 100% sure, but this is what I have so far. E to the x times a sum from j equals 0 to omega of g omega minus 1 comma j times f of j. And if you were to plug in omega, it should work out, and I can just look at that. Well, actually, technically, this is just going to become, yeah, I mean, that's right, that will work. So this is my first prototype. I'm actually going to keep working on this, and maybe by the time I have to do something else, I'll have a better version of this. But that'll be the end for today. This was Deep Thoughts D, and I'll see you next time.